A robot video goes viral because the motion looks human. The harder question is, what had to work in the real world for that 10-second clip to happen at all? Today we unpack the mechanical story behind the demo, specifically how engineers are trading heavy lasers for lightweight sensors to solve a critical mass problem. You might assume removing LiDAR from a rover is a cost-cutting downgrade, like swapping a high-end camera for a phone. The reality is the opposite. In extreme environments like space or rough industrial terrain, those heavy sensor units act as mission killers rather than upgrades. For decades, autonomous rovers relied on brute force scanning to see where they were going. A traditional LiDAR unit works by firing thousands of laser pulses per second and timing their return to build a dense point cloud. It is incredibly accurate for safety in controlled environments like self-driving cars on flat highways. However, these systems are massive power hogs and weigh dozens of pounds. In the context of long-range exploration or mobile robotics where every gram counts, this hardware creates an impossible bottleneck. A rover carrying such heavy sensors cannot travel far before its batteries deplete or it becomes too unstable to traverse rough ground. Current relative navigation methods using standard LiDAR effectively limit autonomous drives to roughly 200 to 400 meters before error accumulation forces a human operator on Earth to intervene and correct the course. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates a hard ceiling on exploration. If we want rovers to travel thousands of kilometers across unknown terrain without constant handholding, we cannot rely on heavy scanning hardware. The engineering shift is not about replacing quality with cheap plastic, it is about trading brute force scanning for intelligent sampling. Researchers are now moving away from systems that try to scan every single pixel and toward methods that use lightweight, custom point cloud sensors, often utilizing 3D printed optical geometries or camera-only setups. This drastic reduction in mass and power draw allows the vehicle to carry more fuel or batteries while maintaining the ability to perceive terrain hazards with high precision. The mechanism behind this breakthrough is a technique called adaptive LiDAR sampling. Instead of firing lasers at every point on the ground, new frameworks use an ensemble of predictors to identify areas where the terrain has high variance, places that are complex, steep, or completely unknown. The system focuses its measurement resources only on these difficult spots and skips over flat, safe ground it already understands. This approach achieves depth completion accuracy comparable to full scans while requiring 4 to 10 times fewer measurements. It effectively creates a dense, usable map from sparse data points generated by lightweight sensors, filtering out noise without needing heavy calibration equipment or massive power budgets. To replace the need for these heavy lasers in absolute positioning, we are seeing innovations like Lunar Nav emerge. This system allows rovers to determine their global position with less than 5 meters of error and heading accuracy under 3 degrees even in sunlit areas on the moon. It works by using onboard cameras to detect and match surface craters against orbital databases. The rover looks at its surroundings much like a human does, recognizing landmarks to know exactly where it is without needing a GPS signal or heavy laser scanners. This eliminates the need for ground-in-the-loop updates, enabling long-range autonomy targeting 2,000-kilometer traverses that were previously impossible with standard navigation stacks. The final piece of this puzzle involves multi-agent collaboration, proving that distributed intelligence can outperform any single heavy sensor unit. In scenarios where a single camera's depth estimation is ambiguous or blocked by terrain features, teams of rovers can share specific visual cues rather than raw video feeds, which would consume too much bandwidth. By combining data from multiple lightweight agents, the system resolves occlusions and long-range gaps with a 44% improvement over previous state-of-the-art methods. This proves that we do not need expensive sensors to see the future. We need better math and lighter physics. The era of bigger and heavier is over for scaling missions. True autonomy now comes from the ability to infer depth intelligently rather than just measuring it exhaustively. You don't need a 20-pound brick sensor to achieve high-fidelity mapping anymore. By swapping that heavy hardware for custom-printed lightweight sensors paired with adaptive algorithms, we unlock the potential for global expeditions across thousands of kilometers without needing massive fuel tanks or constant human intervention from Earth. The upgrade is not in having more lasers, It is in knowing exactly which ones to fire and when to trust what your eyes can see. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.